This video is how to determine oxidation numbers in compounds in AP Chemistry. When we look at redox reactions, the telltale sign that it is redox is that there is an exchange of electrons. And if there is an exchange of electrons, the oxidation number of the elements changes. I'll give you an example of what I'm talking about. If we have iron, Fe, and it reacts with oxygen, one of the compounds that it can form is Fe2O3. This substance is commonly known as rust. It's also known as iron 3 oxide. The reason it's called iron 3 is because the positive charge on the iron is 3+. Oxygen, of course, typically forms the 2- ion, as it is in group 16 and gains 2 electrons to complete its valence of 8. Let's take a look at what the charges of the elements are on the left. On the left, as neutral oxygen, oxygen had a charge of 0. And as neutral elemental iron, the charge of the iron is also 0. So the iron goes from 0 to positive 3, and the oxygen goes from 0 to negative 2. To balance this equation, of course, we're going to show 3 oxygens, 3 molecules of oxygen to give us 6 atoms of oxygen, 4 atoms of iron reacting to give us 2 molecules of Fe2O3. In this case, all of the atoms are now balanced. Looking at this, we see that the iron goes from 0 to positive 3, and the oxygen goes from 0 to negative 2. The iron has been oxidized, it has undergone a loss of electrons, and the oxygen has been reduced. It has experienced a gain of electrons. The oxidation number is what I've pointed out here above. For an element that is charged, or for an ion, the oxidation number is the charge of that ion. Clearly in the case on the right, in the iron 3 oxide, we have an ionic compound. Therefore, the oxidation number of the iron is positive 3, and the oxidation number of the oxygen is negative 2. Typically, we write oxidation numbers underneath elements in parentheses. The reason I'm showing iron and oxygen as zeros is because they're both in their elemental state. That's rule number 2. Elements in their elemental state have a 0 oxidation number. So far, we haven't seen much difference between the oxidation number and the charge on the atom. And for many cases you won't. However, within covalent compounds, you often do see a little bit of a difference or a distinction. An example I'll show is carbon dioxide. Now this is a covalent compound, and as such, it's not charged. However, for the sake of what are called oxidation numbers, every atom in every compound is assigned a charge. And that charge is not necessarily representative of reality, but instead it's a way of accounting where the electrons would go if they had to go to one atom or another. For that reason, the most electronegative atoms are the ones which gain electrons. In that case, oxygen, being closer to the upper right-hand side of the periodic table, is the more electronegative. Carbon is the less electronegative. Oxygen is assigned a charge of -2, and if there are 2 oxygens, that means minus 4 is the total negativity associated with both of them, leaving the oxidation number of carbon positive 4. Again, the carbon is not literally positive 4. It's a counting system which says if the carbon dioxide if the electrons in carbon dioxide had to go one way or the other, to which atom would they go? What this system will allow us to do is to try and track where electrons are moving in chemical reactions. An example of where this might be useful is if I react the carbon dioxide with calcium carbonate, calcium oxide. Again, let's do the actual oxidation numbers of these. Now, calcium oxide is an ionic compound, so the oxidation number is the charge on each atom. Calcium being +2 and oxygen being -2. When calcium oxide and carbon dioxide undergo a reaction, they make calcium carbonate, also known as chalk. It's a synthesis reaction in which they combine. If I look at what the atoms are doing in this compound, I'm going to assign them based on their charge again. Calcium, again, is +2. Oxygen is -2, which, when I multiply by 3, gives me a total negativity of -6. If the -6 needs to be balanced with a +6, as the calcium carbonate has an overall charge of 0. So if I must balance this part of the atom or molecule which has -6 over on this side to this side, which will have a +6, that leaves this carbon with a +4. I then look and compare to what each element has done on the left to the right. Calcium started out as +2 and it ended as +2. Oxygen, -2, -2 on the left, and they're all -2 on the right. Finally, carbon, +4 and +4 on the right. Because none of the atoms underwent any change in oxidation, this is not an example of a redox reaction. Redox reactions are examples like shown above, where the charges actually change. Notice that in the reaction above, we went from 0 for both oxygen and iron to +3 and -2. On the bottom, there is no change, so this is not an example of a redox reaction. Not redox, redox. Let's take a look at one more reaction and determine, using this system, whether or not it's redox. Potassium nitrate can decompose with heat, and a triangle over an arrow implies that heat has been applied. It will decompose into potassium oxide, nitrogen gas, and oxygen gas. Let's take a look at what the oxidation numbers of each of these elements are. On the left, we see potassium nitrate, which is an ionic compound. Therefore, potassium in group 1 will have its charge of +1. I next turn to the right and do oxygen. I kind of like working on either end. I go to the most electronegative atom in this group. Oxygen is the strongest electronegative atom between nitrogen and oxygen. It's the stronger. So with each oxygen being -2, that gives O3 a -6, which leaves a -6 to be balanced by +5 with nitrogen. -6 by the oxygens, +1 for potassium, and +5 for nitrogen. I know it seems odd assigning nitrogen a positive charge, but in this system of oxidation numbers, it's what we must do to get an overall charge of 0 for this compound. the sum of the oxidation numbers must equal the charge on the compound. And as I stated before, this is an accounting system. It doesn't necessarily represent the reality of charge distribution within the molecule. It's simply a useful way of analyzing whether or not a reaction is redox. Let's take a look on the right. Potassium oxide is an ionic compound. The potassium always loses 1 electron each, and oxygen always gains 2. That balances to 0. Nitrogen, in its neutral elemental state, is 0, as is oxygen. Let's take a look at if this was redox. First, comparing the potassiums, I see +1 and +1. No change there. Next, I look at the nitrogens. The nitrogen went from +5 to 0. Definite sign of redox. Oxygen went from -2, -2 here, but if we take another look over here, we did see evidence of a change. Let's think about what's happening. If oxygen went from -2 to 0, this oxygen lost electrons. This oxygen underwent oxidation. And if we look at the nitrogen, with +5 going to 0, clearly it's gained electrons. So the nitrogen has gained electrons, it's been reduced, and the oxygen has undergone redox. By losing electrons, it's undergone oxidation. Now let's go over the hard and fast rules that apply in every scenario. Here are the rules for all redox assigning. For group 1 elements, they're always going to be +1 in every compound. Group 2 elements are always going to be +2 in every compound. Fluorine is the most electronegative atom on the periodic table, so fluorine will always be -1. Fluorine will always be -1 because it is most likely to gain an electron or pull an electron from another atom. Oxygen is almost always -2, except with fluorine. In the example of OF2, because fluorine is more electronegative, each fluorine is -1, oxygen would be assigned a +2 state. The only element that can take electrons from oxygen is fluorine. Hydrogen can go either way. When hydrogen is bonded with nonmetals, it's given a +1. For example, H2O. When hydrogen is bonded with oxygen, oxygen is -2, hydrogen is +1. But when hydrogen is bonded to metals, it's given a -1 because it will pull electrons more than metals will. For example, FeH2. In this scenario, hydrogen is -1, and because there are 2 of them, the iron would be +2. And then the last rule is group 17. Group 17, those elements are -1, with most elements except with oxygen. With oxygen, oxygen takes precedence, and oxygen is -2, and the halogen that it's bonded with will take on a positive charge. For example, oxygen and chlorine. Let's take one quick look at the periodic table. Fluorine, chlorine, bromine, iodine, oxygen, nitrogen,